All right, hello. Let's talk chapter two. And we'll just rewind a little bit here and look a little bit at what a scientific hypothesis is. So it's something we covered before, and just to make sure, a hypothesis is a question that can be answered basically yes or no, and is going to be answered using statistics, essentially. That is the idea. And so, a good hypothesis will lead to predictions that can be tested by observation and experimentation. Yeah. And if a hypothesis is not testable, it's not really a scientific hypothesis. You can make hypotheses about other things. You could say, I would hypothesize that beings on other planets would, be made of carbon, like us, and not something else. But until we were to find those beings, we could not actually do the test. And so that is a speculative kind of hypothesis. It's not an actual scientific one. Yeah, so it's got to be testable. We got to stay grounded. So a hypothesis must have two key attributes. One, it's got to be testable. Yeah, we hit that. And two, it has to be falsifiable. So you could make a very broad sort of hypothesis that I don't know that every fried pie tastes good. And the thing is, yeah, you can't test them all. And I guess if you found one, that would falsify it. But tastes good is not a thing that is readily quantifiable. Or rather, you would have to come up with some way to quantify it. Maybe say that modern art is interesting or modern art is not interesting. Neither of those is necessarily testable because they're both really context dependent. So people that are working in the social sciences, or what we might call the soft sciences, yeah, that's being a little mean to them, run into this problem all the time because the things that they are trying to test are, in a large part, things that only exist inside people's minds. And you can do more and less rigorous jobs, but it is not quite as easy, if science can ever be said to be easy, as testing something that's just coming from the natural world. Okay, so yeah, nature, which is like life all together, living together, is governed by biology. So that's understanding how the living things stay living or don't stay living. What's going on at that level. Of course, biology all is based on chemistry, because you got to keep, these are the things that we keep moving around. We keep changing chemicals in order to keep biology running. It's like the gas that runs the car. Physics is underneath that chemistry. Basically, those molecules that we're moving around to keep everything alive exist and obey the laws of physics, some of which we're still just working out. But we can understand them just well enough to kind of get the chemistry going, to kind of get the biology going. So comparing these three sciences, I think the difference between physics and biology, because you can look at the physics of the chemistry of a biological reaction. There are areas where all three of these overlap. But I think the difference is in how much uncertainty you are willing to tolerate. With physics, they want to be able to explain everything, and I mean everything, in a situation using an equation that involves generally maybe a few constants, but usually just simple mathematical operations. And so that's the sort of thing that makes them happy. And very large systems end up being very difficult to model. And so the larger and more complex the system, we have to move to a less certain sort of field like chemistry. And it's weird calling chemistry less certain, but compared to something like quantum physics, it is. It really is. And then from chemistry, we can go up to biology, and you can still be dealing with numbers, and you can try and get down to the physics. But you are going to be dealing with a much more complex system, which is going to involve a lot more uncertainty. And yeah, just where you're functionally comfortable working, that kind of determines which end of this continuum from physics to biology that you work in. I guess something like sociology or psychology would sit on top of biology. And so it's just one step more complex, if you like. All right, and so the little example, which is from an old textbook, but I still like the example, is of these devil's gardens that are made of mostly Duroya trees. And these gardens are actually created by little tiny ants that live in and around the area. And they were trying to figure out how this works, how it's created, but it's a nice little example of a simple experiment. So let's go with this. So, the simple experiment they did was they wanted to figure out, all right, why do we get these areas with only one kind of tree, but that seem to be controlled by ants? Are the ants doing something, or is it the trees that are doing something that attracts the ants? Like, what's going on here? So, to test the hypothesis, sorry, that they were testing is that the ants are directly causing the other kinds of trees to die, that they are actively making certain trees survive and others not survive. So the way they tested this was to take other kinds of trees. So this one is called Cedrela, and they planted it inside the boundaries of this zone that the ants have patrolled, this devil's garden, so to speak. But they put two different kinds of trees inside and two on the outside. And so, they're the same species of tree, but they were treated differently. So on the outside, they've got regular trees just planted in the ground, unprotected. Great. And they got those same trees planted inside the garden. And so if it's the ants or if it's something about being inside the garden, then you would expect this tree to die and this tree to be fine. And these are trees that are taken from the same rainforest, just another part of it. So chances are the nutrition, the soil is probably fine, but this is a good way to tell if the ants are using up something in the area or if the trees are using up something in the area that then doesn't permit other plants to grow. But the other test they did was with two more of the same kind of plant, and I think they did this with multiples, but we're just showing the kind of thing that was tested. And they're putting a thing that's kind of like tar around the base of the tree. You can get this stuff, it's marketed as Tanglefoot, I think, in this country. And the idea is that it keeps not just ants, but any insect from basically crawling up a tree trunk starting at the ground. And so sometimes you will see trees painted in what looks like a little ring of, brown or black sticky tar around the base. And that's what it's for. It's a little insect barrier. Yeah. And so they put this with the insect barrier on the outside just to prove. And so if this one died and this plant was alive, then you could say, well, okay, this barrier that we put on was bad for the plant, and this is not a valid test. But if these two both survived, which they did, then it's the ones inside, the difference between the one inside and the one outside. So this one is effectively the same as this plant. So they're both members of the same species, but ants can climb this one and ants can't climb this one. They get stuck in the tar if they try to climb this one. And so they then put these inside or outside and had a look. And so here is the result. And what they're counting are how many dead leaves that you got on one of these plants after one day of being planted inside. And if they were outside and unprotected or outside and protected, they're both fine. They essentially have no dead leaves. If they were inside but protected, then they were fine. No dead leaves. But if they were inside and not protected, so in the same soil, being surrounded by the same ants, but the ants can get all the way up these trees and they can't get up these, then yeah, lots of dead leaves. Average of something like 11 dead leaves per tree on all the trees that they test. So then you say, okay, what's the mechanism? And from there, they went and looked at these trees, photographed them, they figured it out. What the ants do is they excavate a little hole, and then they're actually injecting from their abdomen a little bit of formic acid into the leaves. And this acid injection literally kills off the leaves so that those trees will die. And it turns out that the ants actually burrow in the wood, if I remember correctly, of the Duroya trees. And it's just the one that they prefer to burrow in. And so rather than try it out and see if some of these other trees might be okay, they just say, no, let's just kill off everything else that is not a Duroya tree. And yeah, we'll live in those, thank you. So there you go. It's a symbiosis between an ant and a tree, and the ants actually very forcibly maintain that symbiosis. But this was all done with a nice little experimental set with 4 experimental groups that together test a hypothesis. They test 2 hypotheses. That's why you need 4 of them. So they test the hypothesis that it's something about being inside that's bad and something about being outside that's good. And if both inside were dying and both outside were good, then that would be the answer. But it also tests whether ants are the thing that's inside that are causing the problem. And that is neatly done by the difference between the ones with tanglefoot on them and the ones that don't have it, that are inside and outside. So it's essentially comparing, the 2 red ones to each other and to the controls outside of that. So it's 2 layers of controls and a very nice experiment. Okay, but we're here really to talk about chemistry. And chemistry is, well, on the surface of it at least, it's pretty simple. So basically, all the atoms want to be like the guys that are over here. And these guys are in this column because they have complete electron shells. And the atoms that are closest to that wonderful state are going to be the ones in this group here and the ones in this group over here. They have either 1 electron too many, these guys, or 1 electron too few. And so the ways that these atoms can end up with the right number of electrons is by sharing. So if they pass 2 electrons back and forth between each other, then it's like they both have filled up, at least temporarily, their outer electron shell, and so they're happy. So through sharing, or sometimes through stealing, that's how these atoms are going to do business. And so, matter is going to be made up of elements. Elements are substances that can't be broken down by normal chemical reactions. But of course, if you put them in a particle collider, you can break atoms down into quarks, and you can break you can break them into all kinds of neat subatomic particles governed by the rules of physics, essentially. All right. And, that was the old names for some of the later atoms, and these are the current names that are given. Okay, so a compound is, 2 things, minimum, that have come together in a fixed ratio. So ideally, a compound is always the same. You'll see some substances, like, let's see, you could say that lignin is a substance. It's one of the sugars that makes up trees, and it's actually a polymer, but the polymer has slightly different versions of a sugar molecule with different linkages between them, hooked up in different ways. And so together, it's mostly units of one thing, but it's not in a fixed ratio, and it doesn't have a fixed size, I guess. So I think a compound has to have a fixed size and fixed set of elements in a fixed ratio. It has to be like an exact combination that you can reproduce, or is, reproducible, at least in theory. And so our example is going to be sodium metal, which is here, chlorine gas, which is here, and table salt. Sodium metal is fairly awesome. If you were to look at the YouTube video that I've put over there in the sidebar, or just search up sodium, metal, water, those 3 words in the YouTube video. There are several on there where you'll see people with varying degrees of caution and good sense tossing sodium into the water. Now, sodium is one of those elements that's right over here. So it has 1 more electron than it is comfortable having. It has 1 electron shell, which is 1 electron knocking around in there, and it would be in a much more stable place if it could jettison that electron. Or, I guess, if it picked up 7 more electrons, but even that is much less stable than getting rid of 1. And so usually, in the world, if you see sodium, it'll have a positive charge because it has lost 1 electron. But not this stuff. This is sodium plus, neutral sodium metal. And so watch what it happens. It kind of first catches on fire and then explodes. And what's actually happening is it's reacting with the water and breaking it down to hydrogen, which I believe is what explodes with the oxygen as kind of a propellant, and the ton of heat that's generated by the interaction. But it's worth a look. Then you got chlorine gas, which is deadly poison. This is like chemical warfare poison, nice sort of yellowish green gas. And weirdly, if you combine this explosive metal and this utterly deadly gas, you get something that makes French fries taste really neat. Yeah, so the point of a compound is that it has characteristics that are different from those of its individual elements. And so sodium plus chlorine equals sodium chloride. There we go. Bam. Got there. Okay. So an atom is made of subatomic particles, of course, and even these subatomic particles are made of other smaller subatomic particles. We're going to have to get into that a little bit in Bio 2, if you are sticking around for Bio 2. The neutrons and protons are really made of the same stuff, which is quarks. And occasionally in this universe, quarks can flip. They can go from being a thing called an up quark to a down quark. And when this happens, and we don't know necessarily why this happens, but we know that in some situations, this definitely happens. It can cause other particles to appear out of nowhere and go shooting off at the speed of light. This is what radioactive decay looks like. And these are the two ways that radioactive decay can happen. So, yeah, very interesting stuff. Anyway, so atoms are composed of these subatomic particles, neutrons and protons, that are mostly unchanging, but occasionally definitely change in certain atoms. Certain atoms predispose some of their protons and neutrons to this particular kind of change. Now on the outside we have our electrons that carry a negative charge and are really tiny compared to the protons and neutrons. So neutrons have no charge, protons have, let's say it together, positive charge, and electrons have a negative charge. Of course they do, of course they do. All right, so this is some of this is like middle school chemistry, I think. So there's a nucleus, that's fine, that's where your protons and neutrons hang out, and you've got electrons around the outside. This is great, that's helium because it's got 2 protons and 2 electrons. That's so this is a neutral helium atom. And yeah, there are different ways to think of it. So you got your Bohr atom over here, where the electrons are in defined shells. This actually does work on a chemical level, and you can kind of make it work on a quantum physics level, as I learned this summer. I never would have suspected. But this is kind of classifying it the way they behave. It's not what they would actually look like if you could take a picture of an atom, which is a thing that you can't do directly, but there are ways to kind of get around this and do it. All kinds of complicated ways. A little closer to reality is that you have a cloud of charge. Now, what you get with the electron shells, and the reason why we're going to show those, is that it allows you to count electrons and figure out their positions. Now, in reality, these shells have different distributions of where the electrons in those shells would like to be most of the time. And yeah, so it's a probability distribution. And it's actually impossible to measure this without affecting the distribution. So yeah, a cloud is definitely the way to go. And so there are energy levels in these electrons. Now, when we get to photosynthesis, we're going to have to think very, very clearly and carefully about energy levels. So you can take a hydrogen atom with 1 electron and 1 proton. And so that electron is somewhere in the cloud around it. And in its ground state, it's going to be in a roughly spherical cloud around the nucleus. But as you put energy into that system, you can put in just energy, like in the form of vibrational energy, or you can put in energy in the form of a photon, like light. You can put in energy lots of different ways. And you can actually increase the energy level of that 1 electron. And when you do that, the electron's distribution, the places where it can go, will actually change. And so you'll get kind of a physical change in the areas where that electron is going to hang out, and also changes in what that electron can do. And these higher energy states are only going to be stable if all the lower energy states are filled up. And this is why chemistry works. We're basically trying to fill up whatever it is the highest energy state is. So we want our highest occupied energy shell to be full, and then that's going to be a stable place. That's where things tend to sit and tend to settle. So yeah, all right, we'll draw our little Bohr style atom. That's BOHR. And so it'll have a first shell, which is called the S shell. And so this is the first S shell, and it's got 2 electrons in there, so that's a 1s2. And then we're going to have our second shell on there, and you're going to get your S and your P. So 1s2, 2s2, and 2p6 is, I believe, how you would describe this particular atom. And so this is neon, 2 full-up shells. I think for our purposes in biology, you're going to get all this good electron shell stuff in chemistry, and so we'll leave that for chemistry. But as far as what you need to know here, you need to know that atoms are going to trade, give up, take, or share electrons so that they can get their last shell full. And so the numbers that it's going to take to fill up those shells are going to be what's written right here on this periodic table. So 2, 10, 18, 36, 54, and 86. And honestly, most of organic chemistry is going to happen at 18 or less. Actually, most of it is going to happen at 10 or less. So 2, 10, and maybe 18. Those are the ones we have to worry about, I would say. Okay, jump ahead. There we go. So yeah, so we're talking about different energy levels of electrons. And so these electrons can absorb energy, and a whole atom can absorb energy. There are different ways that energy can be absorbed. It just can never be created or destroyed. It can change form. And changing form is really neat. So change form, you can have a regular atom, and you can shine a light on it, or a laser, let's say, such that a photon is going to hit this atom. That photon will then cease to exist in this universe. And when it does, the atom is going to, the energy level of that electron is going to jump up. So let's say here we've absorbed 1 photon, here we've absorbed 2 photons, or here we absorbed a much more energetic photon, and we got up to, boom, a higher point. That's fine. But unless there are electrons filling up all the lower points, this higher point is not a stable point. And so eventually that electron is going to drop back down in energy level, either in 2 steps or in 1 big step. And the thing is, when it loses energy, you can't lose energy, just like you can't create energy. So it is going to make a photon that is exactly equal to the amount of energy that it's losing, and that photon is going to go shooting off at the speed of light. So a photon will crash into an atom, disappear from the universe, and the atom will gain energy, and then the atom will lose energy in the form of, it can lose a little bit of heat or something like that if we overshoot this stable point. But then it'll lose that energy, and it will recreate a photon with exactly this amount of energy. And figuring out where these exact points are, exact amounts of energy that atoms can take in and lose, that is quantum physics. And ultimately, that is what is going to determine how biology works. So that's kind of fascinating, I think, and something we don't need right now, but we're going to go toward that as we go on through the term. Okay, so our big key numbers were 2 electrons in the first shell, 8 in the second shell. So, but you can't fill the second shell unless the first shell is full. So yeah, basically 2, 10, 18, those are going to be our important stable points. And the electrons in the outermost shell, however many there are going to be called valence electrons, and this whole shell is going to be called a valence shell. That's just whatever the atom has to work with. So yeah, if you're interested, this is what some of those orbitals actually look like. So where the atoms, or rather the electrons, will spend their time. And so you've got your s, p, d, and f orbitals, and so the first shell only has an s orbital. And so yeah, that's the distribution. You're going to have a sphere. And then the 2s, if we get up to there, they're going to occupy a sphere around this one. And then if you get up to the 2p, which is where we actually have it full, then you'll have this kind of distribution. And we're looking at, I believe, atoms with different spins occupying different zones here. I think that's what the yellow and purple colors are. And so on for the third shell and fourth shell, just like that. Yeah, and so you'll actually have these different patterns. And you can see this in a hydrogen atom, that where you excite this up and up and up. I believe these are all solutions to the Schrodinger equation um, for where the electrons basically are on an atom. And so, yeah, this is all still hydrogen. But if you were to bump hydrogen up to a mode that looked something like that, you would probably have an atom that could make combinations at this end, and at these two sides, which are kind of pointed back into the screen, I believe, which is why they look like that. And so on. If you had something like this, it could probably make two connections. If you have something like this, it can probably only make one connection. So the energy state of that electron will in some way determine the ways that it can interact with the world. And if, yeah, understanding that kind of gives you the atomic properties, which gives you all the rest of it. So, all right, fine. So everybody wants to be like these guys over here at the end: helium, neon, argon. And so you got some like fluorine, and look, it's got 2 on the inside and 1, 2, 3, 4, 5, 6, 7 on the outside. It just needs 1 atom. So if it steals it from something like a sodium over here, or chlorine is also 1 atom short of a party, chlorine will happily steal 1 from something like a sodium, and you'll have sodium with a positive charge and chlorine with a negative charge. They'll still hang out together. They'll be sodium chloride. But if you were to dissolve this in water, the chlorine would keep that electron, and the sodium would be missing that electron. So, there you go. What's the atomic number of silicon? So the atomic number is the number of protons it has and the number of electrons it has at neutral charge. So let's look. Do you see silicon? I see it. Look, it's right there. 14. And so what are our stable points? So our nearest stable points are 10 and 18. And so what 14 tells us is that silicon has got to make 4 bonds and either share out 4 of its electrons. I guess it could lose 4 electrons, but that wouldn't be a very stable thing because it's got all those protons on the inside. So that would be, pretty unstable. But yeah, if it shares 4 electrons, makes 4 separate bonds, then it can reach stability, and it can be like argon, that's who you want to be like. Same deal with carbon. Look, it's got 4 in that valence shell, and so carbon is going to form 4 bonds. Nitrogen is short 3, so it's going to form 3 bonds. Oxygen is missing 2, it's going to form 2 bonds, just like that. And those atoms, carbon, nitrogen, and oxygen, are the main drivers of all of biology, along with hydrogen up here. That's what organic compounds are made of, for the most part, with a little bit of sulfur, a little bit of phosphorus in there. But you can figure out how those combine pretty easily. Okay, so how many protons and neutrons in silicon? 14 protons, and we'd have to figure out how many neutrons it has, but protons and electrons should be 14 of each unless it has a charge. Yeah, in which case it'll be fewer electrons or more electrons. Because you can't change the nucleus without changing the element, but you can change the number of electrons. That changes the ionic state of the element. How many electron shells are normally occupied? Well, you got 2 that are fully occupied, the 1s and the second complete shell, which is a 2s and a 2p together. What's not fully occupied? Well, that entire third shell is only halfway full, so that's where we need to go. How many valence electrons? 1, 2, 3, 4 around the edge, so I see 4. Perfect. Okay. Polar and nonpolar. So nonpolar means that an electron is going to spend even amounts of time, same amount of time with one atom as with the other. So if you have 2 chlorine atoms sharing a bond, Cl2, then these electrons are not going to be pulled more to one than the other because they're both chlorine. They both have exactly the same pull, and so bam, like in an oxygen molecule, that's O2. They are both equally tugging on those electrons. Same thing with a hydrogen, H2. Same thing with nitrogen, N2. So yeah, those are nonpolar covalent bonds. And nonpolar bonds like to hang out with other nonpolar bonds. That's just how they are. So things like oil are going to have bonds like this that are nonpolar and are basically evenly sharing. They're just fair. Polar or hydrophilic bonds are going to be when one of these atoms is pulling significantly harder on the electron than the other. And so the electron is going to spend a lot of time with one atom and not much time with the other. And so hydrogen here had one electron. Chlorine was short one electron, but when they form HCl, they're actually going to have their electrons spend most of their time around chlorine and pretty much no time around hydrogen. They're much less time. It's still a bond. They are still sharing those electrons. But because the electron's going to spend a lot of time toward this side, you're going to have a small positive charge. That's what that little curly thing, it's a lowercase Greek d, lowercase delta. And this side will be a little bit positive. And so if you have molecules like that with a positive side and a negative side, they're going to like hanging out with water because water is just like that. And so, yeah, but either way, these are both covalent bonds. This one's nonpolar, this one is polar. So this one would be hydrophobic, this one would be hydrophilic. And then you've got ionic bonds. Now, ionic bonds will actually break down in water for the most part, I think. And so these ionic bonds are actually basically stealing an electron from one to the other, but then having a positive and negative charged atom that kind of stick together. All right, and that's the end of our little chemistry demonstration.